Mm, This is ME 5390 Advanced Thermal Design. This is a lecture. Uh, well, I'd like to just briefly indicate a few things, not detail, about the homework, and then I'd like to move on chapter 3. You might have some question or problem.
Post the solutions.
Yeah, I'm gonna post the solution so you can look at it. Okay. And then probably sometime before the midterm, I like to go over. Okay. 2.9 is um, something like pre-convection heat sink. We have dimensions. So as I mentioned, you can look up the single fin uh, approximation actually. Okay, if you have a SCAD, you can look at it multiple fins, but so you can design single fin, and then question is what would be spacing, okay? Optimum spacing. So so optimum spacing is you have to look up Allen bars. Uh, I'm sorry. Uh, Allen bars, Rayleigh number, um, and heat transfer, Allen bars. So once you have that, then you can look at the optimal spacing. So you can have profile length and thickness. I told you single fin and optimum, but we need one more. What is more? I'm sorry. Hmm. Uh, the according to this is one according to the theory, pre-convection only. Multiple fin, the optimum space is this is actually for maximum heat transfer. Maximum what it's a little no, without constraint. I'm sorry. It's very confusing. Without constraint, yes. So it's very careful. This is only without the constraint maximum. If there's any constraint, no, we have to find. I think that's you have to little recognize. This is very dangerous assumption because only without the constraint only. So with some constraint, you have to look up the thickness. Optimum is fine, but the thickness, okay, profile and that's A and B. And 211, this is actually a flow is here, and this is about LB. We don't know R2. We don't know. So it's hard to figure out the optimum thickness because we don't know the base width for flow. So I suggested LB is maybe you can start. You can start. This is not correct. Whatever you assume and get the optimum and calculate the calculation. Then find the R2. Once you have R2, then what is look at that. The L,
So I have a quick question.
yeah,
So the starting LB, you made a comment about double the diameter, or is it double the radius that you meant?
that's the probably diameter is too big.
Right. Well, you meant to
So
assume to start
because
with
the
an
shape,
assumption.
the flow, and then it's I don't know. Nobody knows. I assume R2 maybe even eventually we look at it. So we don't know R2, and then we don't know, but we have to start.
Would you
So
start with double R1?
what is a WR1?
Double,
Uh,
like double.
R1 is too small. No, no.
Right.
R1
Well,
is
I mean, well, R1 was 10 millimeters, so you doubled it, and now it's 20 was an assumption.
well, yeah, yeah. Your assumption, as long as you assume, fine. Yeah, you can
Okay.
start. You can start actually. Okay.
Okay.
Um, so I would, if I grade, I should be okay because as long as you assume and proceed, and that's fine. But the real design, you have to iterate, come back and check your assumption, and if it is too far, you have to repeat. Do you understand or not?
Yes, because
Yeah, yeah.
I had gone back and the Reynolds number became turbulent
Oh,
with
yeah,
the
yeah.
new R2, so I didn't know if that was because I ended up getting R2 of about 50 once I went back
Hmm.
from the 20
Okay.
because I compared it to the charts with
Yeah,
V and
yeah.
W.
Okay.
And when I got that, I got 50 millimeter, like 54 millimeters, I think, for
Mm-hmm.
the new R2 with assuming 20 to begin with.
Mm-hmm. Mm-hmm. Yes.
So,
There's some uncertainty once your assumption is too far from the R2. I think
okay,
R2 is reasonable. I think I'm not quite sure. Nobody studied this. Okay,
okay.
so we in this course maybe try to get the R2, but
Would you then do another iteration if you're too far off? Is what you're
no,
saying?
no, no. In this course is just assuming around the about the, yeah, about whatever 30 millimeter and one just the process is enough. I like to see how you work on
Okay, I see.
that. Yeah,
Do you
but I
show
let you
that? Do you
understand.
show? Yeah, I understand. Do you show that in your solutions?
Yeah,
Okay.
I will show you. Even my solution is only one iteration only.
Right, and that's what the book did, but the book was very close to their assumption.
Yeah, yes, 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 yes.
So when I'm off by 30 millimeters, that's not very close.
Yeah,
But
but it makes sense. Do you understand? This is R
yeah,
two, and then flow. Once you how to make a flow and then determine average RLB is a that's only we can do it. I think. Yeah. So there's some uncertainty. Don't worry. As long as you understand, you can say something. I understand. Then it's fine. Just to show what um, we have to assume in the beginning. Um, so anyhow, um, in whatever the point is, um, we're able to design, right? Optimize. Yes. Answer is yes. Try to figure out optimal uh, optimize. Okay. B, not the B, R2, T, and O, and the Z, OPT, something like that. Try to. Okay. So we have tools to optimize multiple radial fin. Would that be interesting? This is one of yeah, interest, kind of optimize. Otherwise, you guess and we don't know how to optimize it. It's very difficult. Even numerical. Um, do you think you can find the numerical optimal? No, I don't think so. Because numerical, there is a very limited one computation. It takes a long time. One dimension. Okay, one process takes a long time, even numerical. So how you can get to optimize it? 10 times, 20 times, you're gonna run it? Impossible. The time clicking waste of time. So optimum design is a really we have to solve analytically. That's why still analytically we have to solve it. Numerical is very limited. Once we have design, and then numerically we can confirm, but uh, that's why the powerful analytically 1,000 times uh, we don't have to, because we have theory, and then we can come up with a very immediately optimal design, although we have some assumptions. Okay, so you have to understand um, this is very difficult to design optimal. But this is a very typical application, radial fin. Uh, and the square fin, we can do it. Okay, square. How? How to do it? Is it's a we assume circle, but the same area. Okay, so a little difference, off, on, off. but the same area, and then convert circular radial fin from square fin and optimize. It works actually because you look at it, plus minus, there's very close radial fin. We can come up with it. So the practical square fin using the circular fin, and you got the R2, and then convert to real dimension. But the area must be the same. Okay, so that we can design whatever the distance. So there is an example in the book, okay, using this technique. I will come back. Before the midterm, this problem, okay, to 8 to 9 to 11, I will come back. But today, I'm going to move on chapter 3, okay? We are moving a little fast because I am going to up to chapter at least 5. Okay, I'd like to discuss chapter 5 to this semester because chapter 4 is challenging. Now, the heat pipe is something like interesting device. It's a slender pipe. It's a pipe, something like that, 1 millimeter, 2 millimeter. It's all kind of size, and inside is a fluid. Okay, it's a liquid or vapor or whatever. It depends on the temperature. This fluid, and one side is cooling. One side is cooling, and the other side is heating. Okay, that's an application. So one side is cooling, is temperature is lower, and the heating is temperature is higher. So it depends on the fluid, but some portion is vapor, some portion is liquid, if and then evaporation, because possibly it depends on the temperature, basically. That's why we're gonna design the heat, temperature, and the fluid. Okay, so that evaporation taking place. That's the design. Okay, so once there's evaporation taking place, and here is condensation taking place because of losing heat. So that the pressure drops, pressure increase, naturally vapor flows so high speed. Okay, think about whatever pipe and pressure drop suddenly and pressure increase and has to move. So if one is condensate, then somehow we will discuss this condensate should move. We will discuss that, how, but it should move and then evaporate. So it's a circulating. We call the wake, something like a wake. using the capillary effect. The liquid is moving and evaporation and moving the vapor and condensation. It's a continuous cycling. What happened is a phase change happen here and here. So phase change is the most important phenomena here. Condensation, evaporation, condensation, evaporation. So latent heat, once it is a latent heat, is about 10 times of a single phase. 10 times, very high enthalpy, very high. Okay, so that since there is a phase change taking place, so huge of heat is flowing here and here because nature of enthalpy. Okay, from liquid to vapor, vapor to liquid. That causes unbelievably high heat flow. Small, but heat flow, very high. So it's very useful. Somewhere we need a high heat transfer, much higher than copper. Copper is the most highest thermal conductivity. But it turns out copper, the thermal conductivity of a Cu, copper is about 400. The heat pipe, assuming effective, like a conduction. So heat pipe, based on the conductivity, it's a very interesting. And then we can compare how good. 1,000? No. 10,000? Or even 100,000. That's a so huge superconductivity using heat pipe. So look at that. That's what I said. So heat pipe is almost a superconductivity. So it may be useful. Okay. No any other material can be higher than 400. But the heat pipe, it can go 100,000 easily. So that we're gonna study and what's going on. Okay, so that's a evaporator and condenser, and here no heat transfer. Sometimes adiabatic section. Okay, so we if there is a adiabatic section, there's no heat transfer. Something like that. So when we have a bubble, think about vapor. Suppose vapor and air are different, first of all, okay? Air, the gas, okay, air is a gas. The vapor and the gas is different. I think because the vapor is a pure usually, so that follows thermodynamic property, phase change expected. But usually gas is not phase changing easily taking place. Yes, but very different thermodynamic, because not only one substance, a number of substance, like air. Air is a number of substance. So it's a very difficult to liquefy. Yes, but it's a different story. So vapor is based on the thermodynamic pressure and temperature and vapor, like ideal, we have some prediction. Okay, so that's a big difference between vapor and gas. Suppose any kind of vapor, substance, liquid, and there is a bubble, suppose, possible bubble, radius r. Okay, so according to this is a definition of surface tension. Surface tension is along with the surface. Okay, so if this is a half bubble, then the interface is 2 pi r and surface tension, so that we can calculate the forces. That's the in the surface tension definition. And also, so that's why we write, okay, tension on the circumference. No, imaginary cut, pi, 2 pi r, and sigma. It's a surface tension. Sigma is, we know that. This is a property. But this one must be the same as the pressure inside. Okay, but according to geometry, there's angle is the same as pressure on the surface of hemisphere. Same, this P, actually. It should be the same. So this is easy. We can calculate the pressure and area. That is the force. So this force tension and this must be same. Okay, that's why we have here inside and outside heat balance, and that force is equate with that surface tension, and we come up with equations. That's known as a Young-Laplace equation. That's very interesting. This is true. P1, P2. P1 is inside. P2 is outside. So always the curvature inside is higher than outside because of tension. So inside is higher. How much higher? 2 sigma over r. The radius is smaller, more pressure difference between 1 and 2. I told you it doesn't matter with the vapor liquid. In opposite the same. As long as the curvature, this is 1, this is 2. So pressure 1 inside minus pressure, if this is a radius, 2, and then the surface, because of something phase, vapor, liquid, or liquid, vapor, it doesn't matter. So property divided by r. So if r is small, the pressure difference is huge according to Young's Laplace. This is so important. You should and this is most important equations in this phenomena. Okay, so keep in mind this Laplace equation, pressure 1 and 2, and then we can apply these anywhere capillary rise, different size, large and small. Then there is something height changes. You know that capillary. Why capillary effect? Because tension. Look at the tension. Surface tension draws. So the weight and the tension are balanced. The smaller, more higher. That's the capillary. And this capillary rise can supply the water. I think one of the tallest tree, 300 feet tall tree can supply the water. 300 feet, just the capillary effect, believe it or not. Okay, and it turns out the human brain so thin, micron, so thin. So the pump, hot pump cannot supply the water to the brain. How? Capillary effect. It's just the flows, whatever, because of capillary, not the pump. Originally, is starting with the pump, but later it's so thin brain. So important surface tension. My. Yeah, I don't want to delete it. So if you include the some angle, contact angle, and so we can discuss if we include some contact angle, like liquid paper. The liquid side angle is a contact angle. Okay, we call it contact. Yeah, contact angle. Yeah, that's what I'm talking about, contact angle setup. So this contact angle depend on the property and the surface, all kind of. If contact angle is less than the 90, it kind of wet. This liquid is wet on the surface. If contact angle is greater than 90, it's a non-wetting. Okay. So non-wetting, wetting, and the non-wetting depend on the contact angle. Okay. So soap. Imagine you drop droplet of water. What do you expect the shape of a droplet on the soap? Just a speculation. Wetting or non-wetting? Answer. Is that too difficult question? You everybody use soap. Shower. I'm talking about it.
Would it be wetting?
Why do you think so? Because we don't know.
Since
Yeah.
it, I mean, it isn't hydrophobic, so it's gonna have water like a half droplet.
Yeah. I think you're right. It got a wet. Something like that. The contact angle should be less than 90. Is a way wetting. So that we can clean the body grease because of that wetting on the soap, so that we can clean. Okay, that's the why we use soap. You're right, wetting. How about the car? Um, Shiny. You waxed. So you
Might be
drop
non-wetting.
you drop water droplet. Is wetting or not wetting?
Would it be not wetting?
Yes, you're right. That's the purpose, on purpose. So that the rain or whatever, it's just a roll over. You see, on the wax, it's not wetting, rolls. So that maintain the cleanness. Wax is not the stain forms on the car. So it's none. Make sense? So
Yeah.
surface, yeah, it's a wetting. So some property we use, believe or not, surface tension is very important. So it's a matter of contact angles. Um, so there is a surface tension, like a droplet of water, or whatever, liquid water. We know that the faucet water, it naturally become droplet. Yes or no? Yes, because of surface tension. Okay, there is a forces, tension forces. So once it's a droplet, the inside is 1, outside is 2. Pressure difference, P1 minus P2. Which pressure is higher? Water droplet. Can you answer? Inside or outside? Answer? I'm checking your under.
Inside.
Which one is higher?
Inside?
Inside.
That's
Yes.
right.
Yes. Inside is higher than outside. How? Why? Do you know why? Any equation you can use it? Young's Laplace equation. P1, P2 is 2 sigma R. You have to use it. Okay? Now, a little bit some story about this. My story, actually. um, suppose there was a accident. The helicopters air altitude, some altitude, moving, moving. And there was a crash. Suddenly. So investigating, there's no reason, no mechanical failure, no pilot mistake, but it's crashed. They was looking for a reason. I'm gonna the the uh, the blade propeller. There is a droplet of mist of water possible, very small, micron. Okay, this micron water, and the temperature was cold. The temperature is much colder than icing because of temperature. So it may be freeze, yeah, maybe. But what happened is the surface tension so small radius. So P1, P2 is 2 sigma water of R is micron, huge pressure difference inside, high. So even icing outside, temperature is very low, but still inside, because of pressure high, it can be liquid forms, possible. It's just physics, thermodynamics, because of pressure. So it is liquid as long as it is spherical. But when this micro droplet hit propeller blade, it loses sphericity. Once it loses sphericity, freezes. Immediately freezes, freeze. So that the propeller lose the balance, immediately lose the balance once it's water freezes and crashes. This is my interpretation. No one, I never read, I don't know, I couldn't publish, but possible. But once it's crash on ground, it melts. So nobody knows what happened. Possibly. Okay. So this might happen not only helicopter, the same things, plane, jet. Unfortunate the mist and temperature, a coincidence, and this might happen. So when they can see ice accumulate on the plane, it's very dangerous. But better than the helicopter. Helicopter is rotating, immediately lose balance. But the plane is better, but still is problem, dangerous. So the Young's Laplace equations is very weird in the air, something like that. Okay, this is my story or my interpretation. May not, but very possible interpretation of a helicopter crash. Okay, a sudden situation. I don't know. The people recognize because I never reported. I never read it, but they already know it. Maybe they have to warning this situation. Okay. Any question? Do you understand that? So sphericity, it is important. Is lose sphericity, freezes, freeze because of surface tension, no more. Let me so let's a little bit move more about heat pipe. There is a limitation design. This is usually a very low temperature. No. So sonic, capillary, boiling, entrainment, 1, 2, 3, 4. So what is the sonic is the vapor flow reaches sound velocity and the shock wave. So no more supply. It's a shock. So that's the limit of vapor flow when it reaches a shock wave. Okay. Entrainment is if you look the flow, this is weak, this is vapor, this is a weak liquid flow, so it's a counterflow. Look at that, vapor and the liquid, so that it is entrainment might happen. This vapor, then it will flood. It is no good. It might happen. Entrainment is the vapor carries liquid from the wick. And then boiling, capillary is we will discuss. There is a limitation, capillary, okay? the size, wise, we will discuss. But what is a boiling? I think it's a little difficult to understand. Here, evaporation and condensation. It's a liquid flow, vapor flow. We like to evaporation taking place at the liquid surface, evaporation. But this surface liquid boiling is vapor forms on the surface rather than interface evaporation. So it's different. Boiling and the evaporation are different. The boiling, the vapor block the liquid flow. So that's the limitation. No good. No good. No good. This is no good. Once it's happened, no good. You have to maintain under this limit. So it's very important to calculate this limitation. And so design issues. Let me a little concept of a heat pipe. Okay. So condenser and evaporator. I told you evaporation taking place and the condensation taking place. Once it's evaporate, not the boiling. This is, oh my, 1 second. Hello? So boiling is no good. We understand. Boiling is no good. Evaporation, good. So boiling is no good. Once it's curvature, this is weak. Suppose the screen weak. Okay, so wires, we have wires, and then evaporation, it must be some curvature forms because evaporate and pushes. So that I would say curvature inside in the upper 1, curvature outside is 2. Which pressure is higher? You answer 1 or 2. Huh?
Which one's 1 and 2? Are you talking about?
Which pressure is higher? Pressure 1 and pressure 2.
Where's pressure 2? Oh, you're talking about on the evaporation side?
Yeah, whatever, the curvature inside, I1. Anyone? I think you may confusing. Somebody else?
Is 1 higher than 2?
Why?
Because it's inside the curvature.
Yes, that's all. Young's Laplace. 1 should be higher. Once I have curvature, that's the way the curve forms. Okay. Now, so it's vapor now. This is vapor. And condensate, but the vapor, this is vapor until condensation. So this is vapor is gas, kind of. Pressure propagate very fast, moving fast. Okay, if anything drop here, supply. So very temperature pressure drop is small in the vapor side. Okay, so almost let's say here again, but here is a flat condensation, the vapor flat. So it's a flat. One is a condensation taking place. The curve is very flat. Okay. Anyhow, upper is 4, lower is 3, let's say. So between pressure 4 and 3, what is relation pressure 4 and the pressure 3? Anyone say something, the relation? If it is a flat.
Are they the same if it's flat?
Yeah. That's the Laplace. Young's Laplace equation tells us the radius is infinity large, flat. So it's almost the same, 4 and 3. But what happened is here, pressure 1 and the pressure 4 is almost very immediately supply same. This is the same, close to, because of vapor. So 1 is a 4. Okay. So 4 is the same as 3. So now question is pressure 2 and the pressure 3. Which one is higher?
3.
Be 3.
3 must be higher. So
Is that-
so yes
Is
or
that
no?
what creates the liquid flow?
Yes. Interesting. Very interesting. Look at the flow. Gotta flow this way. So that it's a cycling flow vapor inside the pipe. Okay, so we define the effective length is adiabatic and half evaporator, half condenser, because not all is LE, LA, LC is all, but somehow at the end there's a not really heat pipe effect. So we use effective length, and it the turns out now is the pressure difference is the 1 and 2 we call capillary maximum. That's the source. This is 1 and 2. Look at it, 1 and 2. So that's create the maximum pressure 1 and 2 at the evaporator. Then pressure drop at the vapor a little bit. And then liquid pressure drop, some pressure drop. And then this is a normal, actual. Normal, actual is if the pipe is some gravity effect angle, then actual. If the pipe is large, it's possible, then static pressure here and here, some normal. This is a small. Actual, if it is a horizontal, there is no actual. So anyhow, they put the vapor, liquid, normal, and actual. That must be pressure 1 and 2. critical. So we just look at that. Critical. It turns out one is too large. So I told you at the condensation, this is too large. So it must be this. This is critical radius at evaporator between, you know, the,
Is that
the rate.
because the condensation is almost infinity, so it's basically zero?
Yeah. No. Radius is infinity.
That's what I'm saying. The
Yeah.
radius is infinity, so it's basically zero.
Yes. That's why the radius evaporation, this is radius at evaporator, is the source, the distance, the wick or wick distance is the source of a capillary.
Why does that one not use the cosine theta?
Cosine is assuming a hemisphere, we assume. So theta is 0.
Okay.
We assume that.
So
Okay.
you're assuming a full radius.
Yes. Full hemisphere. So no theta on board. Anyhow, that's the capillary maximum. Okay. So
So that's the maximum. So any radius smaller than a hemisphere would be including that, but it
that's the hemisphere is L R over CE. R over CE is hemisphere radius.
but if you go up a half a page to the one you were just looking at,
No, that's the half of a diameter of the hemisphere.
okay, but we don't need to include the angle.
No,
of-
there's no angle. Yeah,
Okay.
perfect. Yeah, perfect hemisphere.
Okay, because
Yeah.
it's the maximum.
Yeah.
Okay.
The angle is 0. It is 0. Okay. That's the maximum. We talk about maximum. So this is we use, and then we have a study of vapor. It's a small, so mostly they neglect it. But I like you look at it using this. Calculate the pressure drop at the vapor side. So friction factor, R over E is a Reynolds number of vapor. Mu is, the viscosity. R is what do you think R over V is? Vapor radius, vapor. And A is a vapor flow area. And the rho V, what do you think rho V? Density of vapor. HFG is enthalpy of phase change. L of E and Q. How we can relate the pressure and the Q is once is evaporation, M dot HFG is Q. I think thermodynamically. Enthalpy change, mass flow rate must be Q. So this is related to rho VA, velocity, density, pressure, whatever. That's why the pressure is related to the pressure is a force. Wait a minute. Anyhow, we're able to relate and so you can calculate. Okay. In this, we we don't know, but if this is the case, Reynolds number is less than 2300. What does it flow pattern? Anyone?
Laminar?
Yes. If laminar, and what is the MA? Do you think?
That's the
Is-
Mach number? Or-
Yes, yes. So is compressible, no, incompressible, something like that. Usually, Reynolds number. Then you use this. Turbulent Mach numbers is greater than this, and use this. The problem is that we don't know until we calculate. So again, you have to assume something, and then pick whatever assume you can pick some value and calculate. Okay, maybe yeah. Now liquid. This is a major, not the paper. It's a small, so you can neglect it. But I like you calculate so that confirm this is very small paper. Now liquid calculate again, mu k is permeability using table. Once you go to table, you can figure out area of wick. Be careful. W is sometimes a wick, sometimes a wire. You have to figure out. And nominal, if there is a significant diameter, otherwise is a very small. Okay, this is a rho of L, not L. Gravity, and phi is also some tilted angle it causes. Now there is a K value for weak permeability. So that what type? There's a many type, but sometimes we just focusing on calculation. Wrapped screen, wrapped screen, something. So that's the wire. This is the assuming wire, critical radius. I think again, this is orientation, P, and actual. Look at that, L, G, and sine phi. So no, don't use. This is approximation. Is you can go always delta T is delta V, delta L, delta P normal, and delta actual for practice purpose. Actually, this is not important, but that's what usually I like you experience what's going on. And then,
You're saying don't use the approximation,
yeah, don't use it.
but so for the delta,
So use this.
okay.
Okay, so you have to calculate all this. So that you can calculate a capillary limit. This will give you capillary limit. Okay?
So that's our the delta P CM.
No,
is
Q
like
max, actually. You can calculate the Q, heat
Okay.
flow maximum from this.
Okay, the QCM.
Yes, QCM, maximum capillary. And then sonic maximum, you can use it. And entrainment maximum, just to use, what is it? Yeah, use entrainment maximum. As long as you figure out all this, you can figure out. Maybe hydraulic diameter if it is not circular, even. And effective. What is the effective thermal conductivity is weak usually. If you look at the weak is this is a paper. This is a wick. This is a paper. Wick is consist of wire and liquid. So two, but we need thermal conductivity across the wick. That then you have to use effective, we call. So that look at the effective wrap screen is liquid and wick. Two, liquid, wick, and is a porosity. This is you have to porosity, and then you can calculate the effective. Do you understand? Weak thermal conductivity. Anyhow, you can calculate the boiling, everything. We just understand what is the LE here. Answer. Answer, please. L of E. Come on.
Is that the effective length?
No, L of E. Come on. We have L of-
Evaporator length.
Say again?
Length of evaporation.
Length of evaporation. Yes. LA is Los Angeles in California. LC is what?
Length of condensation?
What is the LA? Correct.
Adiabatic length?
Yes, not the Los Angeles. Yeah. I'm kidding. Okay. So what is the KEF now? You tell me. Your KEF here.
Is that the thermal conductivity of
Of
the
what?
effective length?
Yes. So consists of what and what?
Would it be all three?
K effectiveness is a weak actually. Effectiveness thermal conductivity is liquid and weak too, and the porosity. Okay, so you have to calculate. And what is the HFG? Here.
That the enthalpy,
Enthalpy of what?
the fluid and gas?
Yes, latent heat. Okay, enthalpy change, phase change.
From liquid to gas.
Yeah, enthalpy of evaporation, enthalpy of condensation, same. Now, T over V, what do you think of T over V?
Is that the vapor temperature?
Yes. What is the sigma?
Surface tension?
Yes. What is the rho V?
Density of the
Density
vapor?
of the vapor?
Say again?
Density of vapor?
Yes. RV. What is the RV?
Radius of the vapor?
Yes. What is the RI? maybe you have a question. Ri is a pipe, and there is a vapor and the wick. Okay, so vapor diameter, wick diameter. Ri is inside Ri, pipe diameter, radius of pipe. Okay.
So that's the wetted radius, basically?
This is pipe radius inside.
Okay.
Okay. What about the RCE? What's the name of it? Come on. Most important terminology. Most important. You should know that.
That's the radius of the evaporation curve?
No, no, the name is wrong. Anyone?
Capillary.
Yes. The radius of a capillary at the evaporator. Capillary radius at the evaporator, something like that. Important. This is major driving force for capillary limit. Now, R of N is nucleation cavity. So what is a nucleation cavity is the theory of boiling the cavity. This is a solid. The cavity, specific cavity size boiling occurs. Okay, so this cavity size is nucleation radius. It's given with the theory, boiling nucleation theory, 0.254 alone. Then you can calculate the boiling. I think I'm going to have a break. Okay, I'll be back in 10 minutes. See you. Hi, I'm back. Let me see. Like, go over example problem. 3.1, as you see in the textbook. I'm going to read it. A heat pipe for an electronic application uses water as a working fluid. Evaporator is 0.3 meter long. Condenser is another 0.3 meter long. The heat pipe has adiabatic section 0.4 meter long, as shown. This is evaporator, condenser, adiabatic. Okay. Diameter of the vapor spout, we know that, is 20.5 millimeter, and diameter, so something like that. And the wicking structure consists of 2 layers of a number 50 mesh copper screen. So the wicking structure is copper, wire diameter is that. So wire, I think wire diameter, something like that. And heat pipe operate, temperature is 80, horizontal. So there is no phi is 0, horizontal. Determine the capillary sonic entrainment boiling limit. So what we can do is we hydrodynamic property of water at 80 degrees C is operating temperature from table. I think we have to go to I think I forgot to open water. Class. Four, five, 30. Wait a minute. Why we don't have? I think we need a property table. I'm sorry, I should find it before spring. There is a table, appendix A. Open. Yes. water. Hmm. Water. No water there. Property of gas. Sorry. We need not this one. Since yes. E4. I'm sorry. E4. E4. It's I'm looking at not the book copy. It's something. Book copy is more clear, but so we're looking for the water. I'm sorry, I don't have a. I have copy, but I have a little problem looking for water. Yeah, water is there. Water is there. So 80 is here. So we're looking for the property. I think the book is much better. A4. Yeah, water. So this is a surface tension. This is vapor pressure. This is a pressure of vapor, and this is a vapor viscosity. I think that this is viscosity is what is unit. I have to check viscosity. Of
Newtons per meter, or
yeah, and liquid viscosity and thermal conductivity. Liquid. This is K. If you look at the book, thermal conductivity and vapor density, something like that. You have to find it. And the liquid density. This is liquid density and latent heat, HFC. Something like you have to figure out the unit, but this is specific heat. Okay, so I'm gonna go back. You can find the book and then convert some unit. That's what I found. Okay, you have to find the paper, latent heat, liquid density, vapor density, liquid thermal conductivity, and viscosity, vapor, surface tension. Let's look at surface tension 0.06 Newton meter. What is this? Is maybe the unit. Yeah, yes. This is different with the book. So what happened is sigma times 10 to the 2 Newton meter is 6.26. So sigma is 0.06 0.626 Newton meter. You know, you have to convert this to 10 to the minus 2 and become, this is what happened. I think that's something you have to figure out. That's what we have here. And I think that this is the copper. Yeah, copper. The weight is copper. And the length and the effective length, diameter is given. Radius is half of diameter. And the wire diameter and the TW. What is the TW? What do you think TW? Anyone? T of W. Guess.
Is that the wall thickness?
What thickness?
The wall thickness?
Wick? Are you talking about what is the W? Wick or wire?
Wire thickness. The wetted.
No, this is a wick thickness, actually, TW. So if you look at the two layer, there's a two layer of screen, wrapped screen. So this is one, two layer, am I right? Two layer or? Two layer of 50 mesh copper screen. So this is a two layer, one, two layer. And what happened? This is one layer, I think. This is one layer. One layer. So one layer is, what is one layer? I said here says that the wick thickness is 2 dW times 2. What is the dW? Is a wire diameter times 2, and then another times 2. Anyone? What happened? This is one layer. One and one. So two wire diameter. So two layer is you have to multiply by 2. If you understand, say yes.
Yes.
Okay, good.
Yes.
Yeah. That's what happened. The thickness, two layer of, that's the wick thickness. And DI is inside the diameter, okay? dV times 2 TW. I think this is TW. dV. Yeah, this is TW. So 1 TW, 2 TW plus TV. Yes, something I think. And then what is the N is number of, what is the N? Mesh. So 50, number 50 is a number 50 per inch. So per inch times, so you can calculate in meters. 50 per inch. I think that means number 50. Number 50 wire. Number 50 mesh copper. That means so I just convert the total number, how many number per meter. Okay, this is total number of mesh per meters. Okay, now we're gonna use this. Why we don't use a P actual? Anyone? P actual was gone. BL. Why this is? Do you know that?
Because it's horizontal.
Yes, yes. So angle is 0. Okay. So sine phi is 0. Now we just follow the capillary radius, because the number of per meter, number of actually the cavity per meter, that cavity is a radius or diameter, possibly. What do you think in terms of? So it's a diameter. So we divide by 2, it become capillary radius. That's what we talk about, I think. So capillary maximum is 2 sigma. We just calculate. That's the capillary maximum. But the pressure, now we need the Q. How? Let's look at dP B in using this in terms of Q. So we assume actually laminar, assume Maha number is, so that we pick all kind of, we assume laminar. If it is not, we trouble. So we assume, and then in terms of Q, we plug in all the number and equations. And then L, pressure, is also in terms of Q. We have to figure out the K, so calculate the K from tables, and porosity calculated, and then pressure calculate in terms of Q. And then nominal, just use equation. There's no Q, fine. So finally, this is capital, the capillary limit. This is vapor, this is liquid, this is normal. So compared to that, this is so small, vapor. Anyhow, so that we can calculate the Q is 163 watt. This is a capillary limit watt, according to calculation. And then we move on the sonic, 42,000 watt. And entrainment, 7,000, something like that. And the boiling limit, also we calculate 8,000. So total, this is a summary. Capillary limit is 164. Sonic is 42,000. and tray meat is 2.7 thousand, boiling limit 8.5 thousand. So what is interpretation now? Anyone? How you can interpret? Although the requirement is these are the requirement, um, everything looks good, but do you want to say something? What is the actually limitation? If you really say something.
Would it be the lowest or highest value?
I don't know. I don't know. You just try to the meaning of what is the limit, and
It's the lowest value.
so what is that?
Would it be the lowest value because they can't handle any more than that?
Right. You're right. You're right. You cannot handle more than that. That's the limit, because others are way above. So this is the limit. Whatever. That's the according to the capillary. But that's the, if you design like that, that's the limit of what? Heat pipe. Okay? That's the limit of heat pipe. And we were operating is 80, so we calculated or calculated the limitation. If we decrease or increase, the limitation will change. Interesting. If you increase temperature, I just plot it based on the temperature. Anyhow, this is calculated. What we calculated, 164 and 20 something thousand, 20 no 2000, 8,000. Sonic is a 30,000 or something like that. So I was just so curious, is this just a calculation? But well, actually I found experiment 1991. This is a professor in University of Connecticut. They have a measurement, similar, very similar device. That's why I developed example. This is measurement, 80. And the darks are vapor inside. They have measurement. So vapor is pretty much 80, which means the pressure are all constant, because pressure depending on the temperature thermodynamically. So pressure is pretty constant inside, maybe a little bit changing. This is a distance. This is an evaporator here. This is evaporator. This is condenser. So the vapor pressure drop is almost the same. And then the wall temperature is a little about 10 degree because of heater wall degree. And it's almost a little lower in condenser. Anyhow, so we see, and then interesting, they measured limit 225. This is a limit they found. How do they found? Once they reach it, the limit, then no more. They can see experimentally. That's a limit. No increase with anything. So our, I think what was our calculation is 164. There's a little, but that's the beautiful actually, 164 and 225. Huge, I think this is not correctly agreement, but not bad. Not bad. I don't think so. So this works. This type of calculation works. Although reality is a little higher than 100 is nothing compared to 20,000 watt based on calculation. So this is real, even better than the calculated, the maximum, better a little. Anyhow, there was it is now. I like to try to 225 according to temperature high and low. This is measurement pipe, heat pipe. The heat pipe size, we know that. So the heat flow is 225 with the size, diameter, the same diameter. In order to achieve 225, not just the copper, this is a heat pipe, we had to have this high temperature, 1,500. I just the same see. This is, if we want to use copper, we have to have a 1,500 temperature to achieve this heat flux. So what is that? Heat pipe can achieve same heat flow with a small temperature, 10 degree. 10 degree. This temperature is 1,500 degree required to have a same heat flow. That is one of the advantage of heat pipe. I think it's a little hard, but you have to understand. This is we can achieve with a low temperature difference, with high heat flow, possible with the heat pipe. I mean, in a laptop cooling, electronic, the temperature difference is not high, but we need a very high heat transfer. Temperature is not high. Laptop, something we can apply. We don't need 1,000 degree to have a high. So the heat pipe is good for cooling, laptop cooling, turns out. Oh my, today, why is it so tiny? I cannot go. I need, this is how many, 20 minutes? Let me see, I need to go. Yes, I need to go. So what is the heat pipe thermal resistance? The limit is a limit, not the actual heat flow. Only we can estimate the limitation. But how we can handle the actual heat flow? Okay, not the limit. Limit is one thing. So, but below limit, but what is a really heat flow? So we are looking at now. This is a heat pipe and the wick pipe. This is a wick pipe. Do you see that? Pipe, wick, pipe, wick. And then source, high, and the low temperature. So I put the resistance between these two external evaporator, condenser, similar. And the pipe resistance, I'm talking about temperature, between two temperature. And then weak temperature, I said the weak evaporator. Interface we neglect, okay? So small. And this is small, okay, anyhow. So mainly weak condenser, weak pipe, and external. But interesting is that there is some parallel adiabatic and adiabatic at the vapor, adiabatic at the pipe. So like thermal or electrical, it's a similar. So we construct a similar thermal circuit. And the pipe is turns out this resistance. Resistance again is temperature difference 2 over Q, the thermal resistance. So evaporator we can use because of cylindrical. Weak we can use, but weak you have to use effective because two substance, wire and liquid. That's we can handle effectiveness. Now, so we construct the resistance. Total resistance is just if it is a series, just add up pipe, evaporator, weak evaporator. Do you follow me? And weak condenser. If there is no the parallel, yes or no? Series because resistance. But this is in parallel. We have to use parallel. So inverse plus inverse plus inverse adiabatic. This is adiabatic over 1. But we have some calculation and measurement of these three adiabatic, and the air, the adiabatic vapor is so small compared to the pipe and wick. So when we look at vapor, this is so small compared to this. This is so small. So when we compare 1, 2, 3, which one is negligible? This is so small, this is large, this is large. So when we compare the inverse value, which one would be negligible relatively? Come on,
The large one,
which one?
the bigger value.
which one, 그러니까? Vapor adiabatic or pipe adiabatic or weak adiabatic? I know, but you can indicate. Three, 1, 2, 3, inverse value. Which one is negligible? Do you follow me? It's a relative comparative. You have to compare total value, and smaller one is negligible. Which one? This one or this one or this one?
Would it be the pipe?
Yeah, pipe is larger, so inverse is small. Weak is the same. So these two are thousands are smaller than these. So, and then inverse of inverse, it become the vapor. But the vapor adiabatic now, everything it's a vapor adiabatic compared to pipe. When you look at this value, vapor adiabatic is 10 to the minus A compared to pipe 10 to the minus 1, 10 to the, so again, when we compare this value to others, this is negligible again. So total, the parallel components are negligible. So only pipe and condenser, but these two are the same. Pipe, because material is the same, weak. That's why they just use these two. They just use 2 over RPE plus RWE. That's the total. What is total means significant. What is the total is, if you look at what time? If you look at, look at, this is temperature, everything is temperature. So total, if you meaning is temperature difference, these two, this is high, this is low, T high minus TC somewhere in source divided by Q. So once you know that, you can calculate. Wow, you can calculate the heat transfer or temperature difference. So it's so important, total thermal resistance. Okay. So in this example, is the evaporator, adiabatic, and liquid. Some information, and I got the information and the lengths, and then I'm going to use these actually, because this is the same pipe is the same. So 2, and then resistance is just this is the resistance at the pipe. This is resistance at the wick. All we need is effective, and we calculate it. And the effective calculated, actually we need the porosity calculated, and then total calculated. Once I have total, look at that. This is some contact resistance. If there is no contact, but the contact, and then this total is, I'm sorry, between the, I'm sorry, I was wrong. What was wrong was, rather than, this is T infinity, C infinity. So this is THTC, I'm sorry, the contact surface. So this is infinity fluid. So we are interested at the surface temperature, THC. Okay. So total is going to be, if you include, you have to include the external. That's what actually we include. Total. So this is infinity, H. And this is T infinity, C, something like that. So I have to include the contact. I have to include the convection. Also, this is the heat pipe, temperature difference. So plug in, we can calculate, actually, they calculated using a fluid temperature, cold side. This is TH, actually, K, we call silicon, high casing temperature, 26. If we know the Q, Q was given. I think so. Was yes. Heat transfer was given 2 watt. So we use a heat transfer and calculate the temperature of a high surface or silicon temperature. Okay, so I think now assign the homework. I'm gonna little wait homework. 3.1, 3.3, 3.4. I think it's a little. This one is a little challenging, but you have to go through the textbook and figure out. Okay, little challenge. This one we discussed. Okay, due next class. Any question? I'm done. Okay, see you. I'm gonna post. I'm gonna announce it. Homework problems.
Will you post the solutions too for last one?
Yes,
All right,
yes.
thank you.
I'm gonna post the solution, and then next week I'm gonna discuss all the homework problem. Okay, and then following week is midterm. Am I right? Yeah, midterm 1. So next week is a solution discussion day. So whole day we will discuss solution discussion. You can raise question, understanding, but that's the material, I think. Thank you. Bye-bye.